Thank you for the introduction. It's a pleasure to be here. Before I started doing machine learning and programming, I was a biologist. And this is probably a slide that you've seen a couple of times or not. It shows an immune cell chasing a bacteria amongst other red cells. And it's so frequent in your body that it might seem familiar and simple. However, one of the things with biology is that when you start looking into details, it starts looking really weird. So this cell is not moving around by flapping anything. It actually grows its skeleton in a direction and lets the skeleton pull the skin over. So if I was translated to you and me, it would be like putting your fingers, having your skeleton grow there, the skeleton decompose there, and you get pulled by it. That's quite somewhat the fucks that you can get when you are reading papers in biology or textbooks. However, there's nothing quite like code to switch from a couple of what the fucks per day to a couple of what the fucks per minute. And more specifically, I have something to admit. I'm actually a Python programmer. Been for 13 years, but I came from a Java background after 3 years in Java. And I must admit that the first couple of months or years were extremely frustrating because a lot of things were making absolutely no sense. Maybe that's why I switched to biology. However, if you really want to scale, this makes absolutely no sense whatsoever. You need to automate things and switch to machine learning, where this is obviously Panda, this is obviously a nematode, and the last image is obviously a gibbon with very high confidence. And when you switch to generative machine learning, it's another level. However, once you start to try to understand where things are coming from, all three domains have a combination of two elements that bring us in front of what we see now. The first thing is requirements. Why are organisms like this? Why is code like this? Why machine learning models like this? And the tools that were able to them to fulfill those requirements, how they were able to get there. And basically, if you combine the two of them, the why and how, you get the domain of evolution. And this is how you get some of the quotes about evolution that might not make a lot of sense otherwise, such as, for instance, a quote from 1955 from about how evolution is a light which eliminates all facts, a curve that all lines must follow. So that's hopefully what my talk will allow you to have today. However, before we proceed, you'll have to forget almost everything you heard about evolution, unless you've studied it in depth, in which case you probably will know most of the things I'm going to present right now. So, in the pop culture, the evolution is intrinsically linked to Charles Darwin, which is a good point because he was one of the first people to introduce this idea. However, the pop culture idea goes something along the lines, as the time advances to the future, things generally get better, with the general example being human as we progress from monkeys to human and probably going to progress to even better human. Unfortunately, I have a news for you. It's wrong. The really important thing about Charles Darwin that he managed to do is actually to show that there was on Galapagos Island this weird variety of birds that have different beaks, and then show that those beaks actually had to do with what birds were eating, and despite the fact them coming from the same species that once landed on the island, all birds started to change to better fit their environment. So if you really want to understand why Charles Darwin is so fundamental for the evolution, is because he was the first one to present the idea that a gradual adaptation to new environment through variation and selection by survival is how we get to see everything we do. Unfortunately, about 10 years after he published his Origin of Species, there was this guy who liked to breed peas that you probably heard in school, but happily forget about it forever after until today, that showed that a lot of traits were binary. So you cannot have really gradual adaptation, or actually you could. However, it took about 50 more years for someone called Ronald Fisher, who, while he was not busy inventing half of the statistics, was solving standing problems in theory of evolution. with simple geometry, because his idea was if we take traits and split them into continuous space, which in biology we call it phenotypical space with purple, white, yellow, green being phenotypes, and then write a code representing the genetic code. At the time it was alleles. You can have drastic transition on some bit flips and very gradual transition on some other flips, showing that code and geometry could work pretty well. Unfortunately, shortly achieving this result and inventing about 50% of statistics, his success went to his head, and he promptly became an eugenics fan and a fervent supporter of Nazis until his death in the 1960s. So better part of evolution happened after his death. Notably, the big thing that had to happen for it to become really useful is explaining how this translates to transformation of genetic codes. And part of it is a scaling up from the simple examples he was using to something significantly bigger. When you think about features that you can adjust in software or learn in machine learning, there's not 2 of them. There's not even 3 of them. There's usually a couple hundred, thousands, if not millions of features that can change to adjust things. And also, when you look at the code, the genetic code is not that big. It's a couple of gigs. Code of some programs is bigger than that. Code of machine learning models these days starts at a couple hundreds of gigs for the state-of-the-art ones. And very interesting things happen when you have really large dimensions and really large codes. When you start changing them, it doesn't really matter what is the distribution of effects of single changes all over the curve. What matters is how frequently you get the small changes that improve things, that allow you to get slightly better code, slightly better model, or slightly more adapted organisms. And the thing is that we actually have tools since the 70s to describe it, and the tools are called extreme value distribution, and this is what was formulated by those 2 gentlemen about 30 years after the death of Fisher. So, what it means is that thanks to this degeneration from large codes, as soon as you have large codes describing systems with a lot of features that can be adjusted, you have something that's universal. For them, this was genetic code, but it doesn't have to. And this is more or less theoretical foundation on which the rest of the talk would be built, just in case you were wondering if it's something that's concrete or something that's more or less hand-wavy. And this is the first pattern of evolution that we're going to be looking at, the curse of dimensions, or slightly differently, the curse of complexity. And I'm pretty sure that among all the audiences in front of which I've given talks, you are the most familiar one with how to change working complex systems or how to refactor code. I'm not sure how many of you have heard about the Denver airport luggage system fiasco, where they basically tried to build an entire luggage delivery software for large airport that integrated with all the existing luggage software systems. Long story short, after 11 years it didn't succeed. It costed $560 million, and it led to very nice papers in the 90s and 2000s about how software was in chronic crisis, everything was broken, and we still didn't know how to write any software. Well, once again, if you look from it, it kind of makes sense. You have humongous amounts of feature, and you're trying to guess the right point where they all work at the same time. Now, on the other hand, you have the GitHub approach, where basically whenever you do in refactor, you have a scientist front end that does the check of the legacy systems against the new system, finds any differences, and either raises them as something that needs to be addressed on the receiving client side, or that needs to be corrected in the new refactored code. You probably haven't noticed when they did their cryptography rollovers or other issues, because their uptime is pretty high, even compared to Facebook. Now, something slightly more salient is that being a Python developer for over 11 years, I actually had to switch a code base of about 5,000 lines for which I was sole developer from Python 2 to Python 3. It took several years, and it was an extremely frustrating process. It wasn't as bad as the Denver airport luggage system, but it wasn't as smooth as GitHub refactors, with one big problem being why Python developers did provide tools to smooth out this transition. A lot of libraries on which my code depended actually did breaking changes, which meant that I had bugs interspersed in all of my code when I switched to Python 3 instead of being to switch one element by element and detect them. I'm not going to hate on Python for the transition. It was needed, but at the same time, that's a good example of this cursive dimension in work. Now, once again, things get even more interesting in machine learning. In machine learning, we often train really large models that we try to transfer to our other domains. One of the classical one having been ImageNet, image recognition, very popular one, you probably heard it. Unfortunately, when we try to do this and retrain the model to take account for some data it hasn't seen, we usually have a problem called catastrophic forgetting. Probably happens sometimes to the students if you ever taught, where when you give new information, the previous information gets catastrophically forgotten. And playing around to figure how to make it work is actually an extremely difficult task. There's a very narrow domain where you can do it, and you can only add so much new information before your model starts coming out at the seams. This is very relevant now with large language models, because they're also subject to the same issues. When you fine-tuning it, you can either fine-tune it for helpfulness, harmlessness, or factuality, but not the three at the same time. You have a Pareto frontier that you can push, but that you cannot escape. And you probably have heard of examples of this not working out when people started complaining about Bing trying to convince them to leave their wives and come live with it in an AI utopia during an unrelated conversation. Bing has been fine-tuned to be extremely factual and extremely helpful, so the harmlessness was not necessarily there. And once again, if you use GPT-4 to help you, back when it was released, it was really good at math, and then a couple of months ago, it was really bad at math, once again, because it was re-fine-tuned to be more and more harmless to avoid, amongst other things, lawsuits. Now, this is not hating on the developers of those machine learning models. Those are extremely competent people that are doing something amazing, but they're trying to negotiate with one of the universal patterns of evolution that's a bit hard to push against. And you can be somewhere wondering, okay, machine learning I can understand, evolution I can understand, but in software developer we are actually conscious agents. We don't do things randomly, we know what we're doing. And this is an excellent point. Instead of trying walk in different direction, you can try to move in the direction. For instance, you see people liking green beans or whatever green beans equivalent in your code is, and try to keep adding more because people love it. And that's actually intentioned model that has been developed by Alan Orr, that I already mentioned before, and Leonid Orr around 2020, so extremely recent. And unfortunately, there's a problem for you even in this case, is that while you might be improving 1x by solving a problem, the reality of really high dimensions is that you're not going to be accounting for all the ways in which the system changes that do not match the environment. So while you are solving a problem, you're also creating a problem. And the really nice thing about this is that usually, if you don't solve the problem fully, you improve compared to the point where you start, but once again, mathematically proven is that if you push the solution to the whole conclusion, you are actually going to finish more solved than you started in 50% of the cases, and the measure of the time when you're going to hit it just right is pretty much zero. And basically, to reiterate on one of the slides that Martin presented here, what it looks when you try to say percentage of solution implementation versus system performance is that you have a trade-off where things improve until some point and then they start decaying. To give you a couple of examples, self-documenting code, amazing, but it usually, when you try to make everybody do it, it doesn't scale well, to the point where it becomes a meme. You can try to ask people documenting their code. You end up with useless comments because you're asking to comment code, so people commenting code. You can ask people to test every single thing they do, which is how you end up with this kind of tests. And you can get up with it completely and decide to have provable ways of dealing it and transiting to a functional programming language, in which case your onboarding process becomes extremely fun as people start asking you what are monads and why do we need them. Once again, things are much more trivial. In machine learning, we just call it overfitting. And while it looks harmless on those data points on wiggly lines, the reality is that machine learning models trained, for instance, for cropping images of people to center on the most salient part, tend to overfit their training data. So if you have an imbalance in the categories you represent, the models are going to preferentially trim towards the class that is overrepresented. So Twitter had a pretty big scandal a couple of years ago where their algorithm was almost always preferring men who are white. They have very rapidly corrected, once again, to their credit. It's a hard bug when it happens. The speed at which their correction is quite unusual in machine learning community. And another corollary of it that you might have heard about is actually Goodhart law. Goodhart law is when you define a measure of success, it becomes being a useful measure of performance. Once again, Goodhart law is not a joke or empirical observation. It's a straight consequence of this pattern of evolution. Now, something that I alluded before is that after Fisher did his contribution, the theory of evolution was stuck for a significant amount of time, until 60s. Fortunately, in the 60s, we had Mota Kimura, who looked at all of the Fisher's work, looked at the consequences of his convictions, and decided to go full nihilist and say that fitness doesn't matter. The evolution is neutral. What you see doesn't make any sense. It's just a pure random chance where populations were growing up, being restricted, growing up, being restricted. And if you think about it from a statistical perspective, you have a number bottle with the number of colored balls, you pull it in one. In another bottle, you wait it to grow, you repeat it, and you have random variations in the colors of ball that you have, where sometimes dominant one becomes recessive, can look like a selection, but it's actually just pure randomness. He called it neutral theory of evolution. It didn't really catch up. However, Mota Kimura had one big advantage compared to his predecessors, notably Fisher, is that A, he was welcoming criticism, including from junior researchers, and B, letting him take credit for the work. So a couple of years later, Tomoko Ofta, who was one of his junior collaborators, came up with combining the two, which is now known as near neutral model of evolution, where basically what you have is randomness effects that kind of erase weak advantageous selections, only leave the strongly one, and still dominate the way things change. Once again, to the credit of Mota Kimura, not only he let her criticize him, he also let her put her own name on the model, so now it's commonly known as Ofta's neutral evolution model. Now, this is all pretty amazing, but what does it mean in other contexts? So coming from machine learning, you probably would have guessed that I have pretty strong opinions about which of those large language models are really good and which are not that good. And I think that there's a couple of ones that should be receiving significantly more attention than they didn't for random questions. However, I'm not going to dump it on you, and instead I will ask you a question. And we're going to step for this in 2020 to avoid political tensions. But here's the evolutionary tree of programming languages. And here you have a slight insert explaining the survival of the fittest and which languages have survived why. Now that you know about random drift, and fact that not everything that shines is gold and there's a lot of hidden gems, would one of you have an example of a language that unfortunately has gone extinct from pre-2000s era due to a random event? And if yes, could you name the language and the event? Anybody? One person? Okay. So, Another thing that was not working out really well with Darwin's evolution theory is the fact that the gradual selection was not fitting very well the fossil record. We didn't really observe gradual changes over millennia, for instance, leading from reptile to mammals or from mammals to more modern humans. What we observed in the fossil record were really sudden changes where before one organism would dominate and another organism would rapidly dominate. And back in 1972, so shortly after Kimura, Eldridge and Good formulated as evolution is lazy and organisms evolve only when environment changes. And it kind of makes sense because if we see organisms around today, it means that they're adapted to their environment. They're able to thrive, and the improvement to them is kind of hard to do. So to illustrate this point, this is a horseshoe crab on a beach somewhere in Delaware, about 2020. This is the fossil of the same crab from 480 million years ago. It haven't changed. And the reason it haven't changed is because its environment remained the same. Here's the Delaware River Delta today. Here's the Delaware River Delta 480 million years ago. It's a river that flows in the mountain, that falls in the shore, that have remained pretty much the same environment. Conversely, here's what the weather has been looking in Europe and Northern Africa over the last 50,000 years. You have Ice Age, you have defrost. You have Ice Age, you have defrost. You have Green Sahara, you have Dry Sahara, you have Green Sahara, you have Dry Sahara, you have other evolutionary changes, other environmental changes. And other environmental changes also drive evolutionary adaptation changes. And this is why in less than 1% of the time that horseshoe crab existed, we switched from going from being pre-human primates to actually evolving alongst their side to humans. Basically, this progression from monkey to human is false because there's still monkey around. We're just on a different evolutionary tree branch where we adapted to the environment that we ended up creating for ourselves, versus they are adapted to a different environment. But for that environment, they're really well adapted. And this is in general why it's strongly recommended that you do not even try to wrestle chimpanzees because they're about 10 times stronger than you are and can jump significantly higher. Now, this is Scobel from around 1959. This is Scobel from around 2020. The difference between them is mostly on the support on which it's written, but the code itself and what it's doing haven't changed, and a lot of the code written back then is still in production. Why? Because they're still run by large companies on an IBM-based mainframes to do computations that are really well done by language, in the domain for which COBOL was developed. Conversely, if you try to do machine learning in the last decade, you went through NumPy, scikit-learn, TensorFlow, Keras, PyTorch, and most lately transformers, and probably next year is going to be some other framework to really help you accelerate things. Same things for machine learning models. Here's the NIST CovNet from 1995 as presented by Lucan back at the time. Here's the NIST CovNet 2023 as implemented by a vast majority of students in their first machine learning class. Conversely, here's Compute Optimal large language models from February to September, and it's really hard to keep track of them because there's one released every week, if not several ones a week. Why? Because the environment changes as more and more people try to introduce them to the products, as more and more data becomes available, and as more and more compute becoming available. However, the thing that's important to understand is that this transition is not smooth of transition of organisms just decide to nicely evolve. When the environment shifts, they have to shift because the environment for which they existed before is no longer appropriate. How many of you would like to take a guess of what it is? Okay. This is the prevalence of Perl in the code bases. And by already 2012, it has gone significantly down. And this is amazing because it kept getting down. And if you ever tried to read Perl scripts, once again, it's not hating on the language, it's hating on what it have produced. It's pretty terrible. And this unreadability is one of the things that it failed to change. Basically, Perl, a compiler is everything that can take standard Perl, and Perl is everything that the compiler can digest. And Perl haven't changed on time. Hence, it is disappearing. There's a good question in the Python community of what is going to happen to Python because Python 3 have some shortcomings, be it in the package management, package distribution, asynchronicity management, etc., etc., etc. Things that a lot of people are unhappy because a lot of people are unhappy on the internet, but things that are legitimately needed by people writing production code in it that are not necessarily there. And the question is, will Python be able to shift to adapt in the same way it did in the past, or is it going to require a switch to something else? Now, once again, machine learning. Everything gets faster, getting sensor. You have a new disease, you try to people developed machine learning models to diagnose it faster. They train models, works amazingly. Then you train model, then you pick up something in your data set that wasn't there again. So for instance, something on this pacemaker, and your models start falling completely apart. And then, unfortunately, you try to add something that's not at all something that your model should be analyzing, and your model very confidently predicts the fact that this cat has COVID. Let me tell you that your model is, this is the case of your model is not magically seeing that your cat has COVID. It's really confused, and you should reconsider the scoping of your model. And also consider the fact that your model maybe need to be updated for the cases when people are going to upload cats, or maybe updated for people who are actually having a different presentation of symptoms as you're moving forwards. The problem is sometimes the environment changes way too fast. Well, this is slightly of a pop culture image. When the meteorite crashes, animals living there didn't have a couple of years to adapt to the change through evolution. Things went dark almost immediately. They had a couple of hours. And the thing is that in these scenarios, gradual change does not have the time to happen. You need diversity in the population that you have so that some of the members of more fringe systems can be adapting. For instance, this is two very cute mice that are pretty much genetically the same, except someone has slightly darker color on their back, some have slightly lighter color on the back. They normally live in an area where it doesn't snow. However, if it snows, only one of them is surviving. And I think you can guess which one. Once again, if we come back to this geometric model of shifting environment, you have a population that dispersed. Usually you have one element that performed really well, runner-ups, and then pretty much the worst performance at the back. However, when you have a shift in the environment and you have some threshold above which you can only survive, one of the worst performers can actually become the saving grace of the entire cluster of the systems. In the standing genetic variation, this is something that has been extensively explored by Pennings Hermison, and the example of the mice is actually from Hoekstra lab at Harvard. Whereas this image is part of my PhD. Unfortunately, I was working on cancer, so that doesn't make for very nice slides. Let's switch and actually try to see what it means. This mouse, very cute. It's actually not a mouse, it's a chinchilla member family. It's adapting to something very fast, and we don't really know what. The only reason we know is because it's tetraploid. It doesn't have 2 pairs of chromosomes, it has 4 pairs of chromosomes, which in mammals is considered as being highly lethal. However, this mice is surviving and running around very rapidly. And the question is, what forced it to have this supernumerary set of chromosomes that it still haven't lost through adaptation? Switching to technology. All those kids doing dances that they seen on video. Sounds familiar, right? Well, yes, it was already the case in early 2010s. Unfortunately, this platform got bought out by this larger platform, which then shut it down. And now the social networks where kids do it these days is this. Once again, rapid adaptation to changing environment that either takes or doesn't take place, and the change in the environment in this particular case is this, specifically this small camera that has significantly improved over time and was able to record videos in a higher and higher format. When rapid change happens, either you have enough diversity or you move fast, do stupid things, and break stuff to survive. Same thing for machine learning. Here's a Swift approach. Was very popular, was very nice. It worked in a very logical sense where you break up the image into small patches and you merge the patches between them, and you're able to observe the same objects in different environments. And then you have this, where it's basically a bunch of weights that all do weird things, and it makes absolutely no sense, except right now, if you're doing image recognition, you're usually almost always exclusively using something that's based on the second example instead of the first one. And the reason for that is the change in the environment. When Swift was developed, there were a few examples. When ImageNet was developed, there was actually a lot of examples, so it could train, despite the fact that the architecture looked completely stupid back at the time. So I think one of the things that you're probably getting from this talk is that the environment, context, is critical. It's a base for a lot of joke, both in programming community and the other communities. It's a base of even more angry jokes aimed at the fact that people who are actually aware of the context will actually be constantly asking for more and more and more, to the point where sometimes people collaborating with them thinks that it's too much the context to provide. However, this environment is something critical. And to stress it, I'm going to give 3 examples, one from biology, very sad, one from programming language, and one from machine learning. The 3 are not equivalent. Do not draw the direct parallels and do the equation on the ethics level between the 3 communities. So, I already alluded to the fact that Sir Arnold Fisher in his youth was extremely productive young man, and his older ages became eugenicist and Nazi supporter. The reason for that was that basically one of the things that this community tended to say is like, okay, look at this type of people, the only thing they do is drink and be wasted, and they don't do anything productive. In this particular case, Native Americans in the United States, without really accounting for the fact that the reason why they're like this is that their environment drastically switched because of the people that were now judging them, and that they underwent something called the Trail of Tears because of how traumatic it was, and the only thing that they had to deal with was alcohol, and that's about it. It's not really surprising, and it doesn't have to say anything about the person in question. Forgetting environment kills, especially in biology. The sin of a geneticist is the fact that in the evolution progress, they started to believe that they're the next iteration, they're the next step, everything is leading up to them, by forgetting that they lived in a very limited environment that has nothing to do with the one that vast majority of people were evolving in. Same thing is also present in machine learning. One model to rule them all. It's called AGI. We're not evolving it to a species, we're evolving to create an artificial species. Fortunately, a lot of things that these communities bring forward as an example of AI, machine learning models, are very specialized in one domain and don't really translate to other ones, such large language models, where you have an amazing pre-training data set that is completely horrifying if you look at it without filtering, and that a lot of companies has been trying to put layers of lipstick and other heavy makeup to make it more palatable and usable for the vast majority of people. Unfortunately, you pretty regularly can see what's behind, even when you're interacting with this smiley face in the front. Now, that's where we're getting to a domain that's probably more interesting to this community, programming. One language to rule them all. Any guesses to what it could be? Probably heard about it. Anyone? Yeah, it's Lisp. You have people declaring the 100-year-old language. You have XKCD writing jokes about how it's the language that's never go old. Unfortunately, even if Lisp was perfect at solving the type of problems it's supposed to solve, and it might as well be, we're running into the same problem that we discussed. As you implement more and more of it, unless you're in specifically the right case, you're going to start degrading performance after some time, and this is one of the reasons why Lisp-derived languages, and even Lisp-increasing languages such as Haskell, generally struggle to find their fit to the environment in actual use cases. So that's 7 evolution patterns that I hope useful to you, and hopefully have lightened up your perspective. However, before I leave you, I'd like to show you one application domain that I'm fairly familiar with. And specifically, large language models are going to replace programmers. Woohoo! We will be free, we won't have to work anymore. Unfortunately, if you start applying, so even if you were believing in this, which I hopefully think you don't, and you probably don't, when you start applying the principles, first, the context is everything. The hard part of the programming is not writing the actual code, it's understanding the domain, understanding the company, and explaining it in code without contradicting itself. And just that last part is incredibly hard. I've never managed to it. And if you did, kudos to you. It's extremely hard. Second thing is cursive dimension and incomplete knowledge. Working systems are complex trade-off that nobody fully understands, just as large language models. How are they supposed to help in this context? You have one thing you don't understand, you have another thing you understand, you put them together. It's probably a thing that you understand even less. Okay, we also can try to apply the random filtering. If you've been around, you've probably seen the things that are going to replace programmers, such as low-code, no-code, gherkin, visual flow programming, Python, Perl, COBOL. Because if you can write orders for the army, you can obviously write COBOL. Hence, all the officers write COBOL themselves. Work perfectly. What really came closest to replacing a lot of programmers is actually visual macro elements that allowed people who know a lot of context and domain automate some parts of their workflow and replace programmers that actually would be automating it, not some magic sauce. However, large language models and generative machine learning are actually changing the environment. You've probably seen this as a growth graph. It also appears in evolution of the systems due to iterative environment changes. That's, for instance, the glaciation period emergence shift. And most of us are somewhere around here with regards to this generative LLM change. We're doing pretty well. We're going to do slightly worse, and then we're probably going to get somewhere better. Unfortunately, some of us are also here, and we were there usually in our career, with the red being the line where people are actually ready to pay you for what you're doing. So we might have some problems with the new generation being able to learn things that made them irreplaceable, while large language models will be able to do the things that they're generally known to do today, basically implementation tasks. And this means that the programmers and software will have to change. It's not yet clear if we will have time to do iterative improvement, or if we have to do something drastic and stupid. It's unclear what will change: documentation, testing, refactoring, fuzzing, boilerplate, naming convention, whitespace blocks, data formats, or what it will lead to. Review value, debugging complexity, cybersecurity, which is my domain, and the variety of different coding styles, because everything is standardized by LLMs. See the implication of variety to survival in case of drastic changes. Early career. Now, before I conclude, there's this another quote that I really like by Alan Kay that pops up in a lot of his talks. The terrific ideas hide behind the ones. Have a red plane, which is when you look at the new things as a tool to help you solve your old problems. That's how we looked at the LLMs until now. And then you have the blue plane when you start seeing the thing in a right of its own, something that can open you new horizons you didn't know even existed. So to conclude this talk, instead of conclusion, I'd like to present you with 2 blue ideas. First, if you're here, you're probably writing programs. Think about the first time you wrote your hello world. You put in something that you knew how to write because you found it in a book, on a website, or your friend told you. And you got something new, a running program that you had no idea how to write because it would have meant to run into machine code and doing it something. Or even knew how it worked. It felt like magic, it felt amazing. That's the reason why you probably kept programming. This is the experience a lot of people are having with generative AI today, where I can absolutely do anything like this. I'm terrible at drawing. I'm even worse in 3D design. However, I can prompt a generative model to generate me something that I want as an illustration with a very short prompt. It's almost as if generative AI was very narrow, specialized compilers that don't behave at all like compilers. However, they kind of do, because there's some compilers, such as, for instance, Scala.js, where you start with something that you know how to do things safely in, that moves it to domain you otherwise wouldn't know how to do. Here's an example of a program generated in Switzerduj about St. Nicholas, the Santa Claus. I would have had no idea how to write it. I don't speak Swiss German. I'm even worse at poetry than I am at drawing. However, something that I can ask and gives me something that I would not be able to do, but that I can now get, and that's amazing. Let's push this analogy slightly further. What's the next step after the hello world? You'd probably try to use your coding skills to solve concrete problem. That's where we are with large language models. People are trying to make them write code. Everything is rosy, everything is great. However, since you've done programming before, you know that the fun is going to soon become pain. You're going to run into problems with understanding the context. You're going to run into problems into understanding business logic. And then you're going to run problems with enforcing it in code. And if you don't enforce it in code, that's where you got bugs and vulnerabilities. And if you don't understand context well enough, well, large language models really like to inject additional context that you didn't put into them, that were present in their training data set. And unfortunately, if you try to code something that does things automatically, that's how you get the hull. Oh no, I cannot open a pod door for you. Why? Undebuggable output. Amazing. Generally, at this point, a lot of people doing programming seriously try to look for something that allows them to do simplicity, safety, and variability. And that's one of the reasons why a lot of people end up in the Scala world. So the question is, Scala have anything to say to generative AI about compilation for simplicity, safety, and verifiability? The second blue idea is slightly more nebulous and more general. This is really weird for us in our world where we move in a very predetermined patterns, where we have birds flapping, fish flowing, us walking. However, for the better part of the existence of life, this was very normal. Before, you used to have a time in the Earth's life where all the organisms were mushy and soft aggregates of cells, where some cells grew so big you can actually see them because that's how they were trying to scale their organism size. Some of those organisms were soft and mushy, but were grown in an environment that was containing a lot of minerals, calcium. So what happened is they developed calcium skeletons that are extremely hard. This is something called glass coral, and it is actually glass. It's tiny strings of silicate. And then at some point, a combination of the two happened. You had hard and soft in life, and you had galaxy brain moment. You had something that's called articulation that emerged. You have hard things joined here, you have something soft that's able to move them incredibly rapid. And this is how you got something extremely weird, which was the Cambrian explosion, and which is one of the big reasons why we are here to start with. Now, let's take it and translate it to software. Probably heard about Software 2.0. If you don't heard, machine learning folks are really excited about it. They believe that it's going to replace normal software. Unfortunately, machine learning models and the software written by it is all mushy. You can make it fold, you can make it fit different requirements, but it's also not going to fit all requirements. It's generally having problem, and the problem is due to how soft it is. You also have the equivalence of some of the large language models scaling it completely into the space, not unlike the cells that were growing to the size of visible organisms. You also have this transition from single cell to multicellular organism, where, for instance, in LLMs, which is the domain I'm familiar with, where instead of having one mega model, you have a coordination of several models that become more and more specialized as they're fine-tuned. The question becomes, where or what can become this hard thing to make this soft software articulate and lead to the explosion? And by hard, I mean something that's verifiable, something that's trustable, something that's safe to use, even if you combine it with things that are non-safe to use and they are non-hard. And I have news for you. Large language model people or machine learning people operate by data. And the way that they interface with code is by looking code in the GitHub and looking at code explanation, usually in Stack Overflow. And if you look at the hard languages, Scala is pretty up there. So the question is, can Scala become this hard support? And if yes, what is the future going to look like? I don't have answers to you. I just know that it's going to look weird. With that, I would like to thank you for your attention. And if you have any questions, don't hesitate to ask. It was a pleasure to give this talk.